So now we come to the kind of core or central part of this unit, which is looking at collisions and how momentum interacts with that. So what we need to do first is define what a collision is. And so a collision occurs when two or more objects attempt to exist at the same point in space at the same time. And this is kind of the best definition for physics because it helps us talk about things that are actually physics terms, right? A same position, same point at the same time. And it also lets us kind of avoid some of the stickier questions of like, what does it mean for two objects to touch? And it helps it from being a kind of cyclical definition of things collide when they hit each other. Well, what does it mean to hit things? It means to collide. So the simplest explanation here that kind of works for what we're doing is that if two or more objects are trying to move into the same position, they're going to collide. And that works for pretty much everything and doesn't really have a whole lot of downsides other than feeling a little bit clunky. So that's our definition of collisions. So momentum is always conserved in a collision. Doesn't matter what kind of collision or what's going on, but it will always be conserved, and this is because of Newton's third law. So if two things collide, then that means they're going to be, if they're going to collide, they're going to exert a force on each other. And so we know that F of A on B is equal to the negative of F of B on A, right? If they hit each other and they start pushing on each other to change their momentum. And then how long will they affect each other? Well, as long as they're touching. And so that means for however long it is, they're both going to be exerting equal and opposite forces. So in other words, we have F of A on B for some delta T is going to equal to negative F of B on A for same time, same delta T. And this means that we get of the change in momentum of object A is equal to the change in momentum of object B, but negative. In other words, delta P of A plus delta P of B is equal to 0. So in other words, if two objects hit, the total momentum doesn't change. Individual momentum might change, but the total momentum of everything involved in the collision stays a constant. So let's look at an example here. Suppose that a baseball is hit with a bat. I don't think this is the right question I'm going to look at. So it says, suppose, let me fix it with my notes here. Suppose a baseball is hit with a bat. We have this. So what is the change? For the baseball and bat. So you can go back to the previous video, check the kind of calculation there. But basically the change in momentum of the baseball, we can calculate by the force and the time. So for the baseball, delta P is going to equal 480 newtons times 0.017 seconds. And for the bat, delta P will equal, well, it's going to feel a force in the opposite direction, so negative 480 newtons, 0.017 seconds. And so they're going to be the same magnitude, just opposite directions. And so we can see kind of that the momentum is conserved. We could also use this if we knew that initial and the final things, we can calculate missing bits. This is something that as you get practice, you'll want to work with the calculations. So there are some special considerations, and this is where kind of the rubber meets the road and other ways to look at it. So when you're dealing with conservation of momentum, there's two ways to think about it. One is that the total initial momentum should equal the total final momentum. The second way to think about it is the total change in momentum is equal to 0. So in other words, you can have total P initial equals total P final, or you can have total delta P is equal to 0. They're just two ways of looking at it. It's just how you kind of group them together. But sometimes it'll be easier to calculate how much momentum you have before the collision and then set that equal to what you have after the collision. Sometimes it'll be easier to add up all the changes and set them equal to 0. Okay, lastly, we have these two ideas. So an isolated system means that all objects are included and there's no external forces. An open system can include, or there are external forces. So what ends up happening here is if you have an isolated system, that means we can just use conservation of momentum just like this. If you have an open system, you'll have to add the effects of this external force. Now, the external force is going to gain or lose momentum, however much it puts into the system or takes out of the system. But it will look like momentum isn't conserved if we're just considering the system. Same thing with open and closed systems with energy. We can deal with conservation of energy being everything just within the system, or if we have something coming from the outside. But this is just introducing some vocabulary. Basically, instead of saying closed systems with collisions, we'll tend to say isolated systems, meaning everything that's gaining or losing momentum, we're considering it. It's the same thing with energy. Neither of these breaks conservation of momentum. It's just whether all the momentum is conserved within the system or whether it's, some of it goes out of or comes into it from somewhere external. But if we just keep drawing bigger boxes, we'll eventually have a system where all the momentum is conserved within that system.